Hi everybody, Mr. Rubo here. Today we're going to look at some parallel lines and some proofs dealing with parallel lines. So first we have uh, first problem here. It says given that AB is parallel to DC and angle B is congruent to angle D, we want to prove that the two triangles are congruent. So just like always, kind of like plan out our proof. You can see I've already marked what's given. We use the arrows again to denote parallel lines. And then we have the two congruent angles. So with this, we have a few different options, but the big one is that, hold on, lost my cursor. There we go. Because of these parallel lines, we get alternate interior angles. We get all those alternate interior, alternate exterior corresponding. We get those that they're all congruent, which is really helpful. We already have that these are congruent, and then we also have good old reflexive properties. So I'm thinking we're going to prove this by angle, side. But let's take a look. So given, and then here's our alternate interior angles. So here, if we're marking up our diagram as we go, it's that guy and that guy. Okay. And then the other angle is given, and then reflexive property. So this guy, and then finally angle, side of the two triangles we wanted to prove. So nice short proof here. And yeah, shouldn't have been too bad. New thing, again, this parallel lines, that's what we're going to deal a lot with, is using parallel lines in our proofs. Okay. So then the second proof on this page, we have two sets of parallel lines. We want to prove that P is congruent to S. So I'll kind of just, because of where the picture is, I can't really pull this down any farther, but here you go. So you can see we have all the parallel lines marked. And again, because we have transversals, or this one transversal, I should say, we can say alternate interior angles are congruent. Again, it's the reason is if lines are parallel, then alternate interior angles are congruent. This reason is going to be one that we'll use a ton. Okay. I'm not sure why this is right here. I'm going to delete that. So we've shown that PQR, so this angle, and this angle, SRQ, are congruent. And then that was using PQ is congruent to QS, or sorry, parallel to QS. Now let's do PR is parallel to QS. And it's the same reason, we just get two different angles. So we get this one and this one. So now our whole goal, though, was to prove that the two angles, the last two angles, are congruent. So we could do it one of two ways. We can go ahead and just prove the two triangles are congruent, which is easy enough, right? Which is probably better in the long run, just because you could use more things then. You could use this proof a little differently. But the other way we could have done is also no choice theorem. But again, adds a few extra steps, but it is a better proof because then we can actually now prove not only are these two angles congruent, we can also say, corresponding sides are congruent too. So that's why that one's a little bit more helpful doing it that way. All right. And then our last one on this page, we get this time no longer the just straight quadrilateral. Now we just have lines, right? So we have A is parallel to B, and then C is parallel to D. So you can, again, see the arrows denoting that. And we want to prove that angle 1 is congruent to angle 3. So let's go ahead and kind of think about this time, though. This picture, we actually have corresponding angles. We have alternate exterior angles. We have alternate interior angles, right? So we can actually mark up this diagram a ton, and I would not advise against that, but it will get messy if you mark every single thing you know on this diagram. But we're just trying to show that angle 1 is congruent to angle 3. So if you look between A and B to go from 1 to 2, those are corresponding angles. And then if you look from 2 to 3, those are also corresponding angles with just respect to the other parallel lines. And then we're going to use some transitive properties is my initial thought when I look at this. So look at that. Given A is parallel to B, and angle 1 is congruent to angle 2. Again, similar reason to what we've used before. If lines are parallel, then corresponding angles are congruent. Awesome. Then same exact thing to say 2 is congruent to 3. And then our last thing here is that transitive property, right? Angle 1 is congruent to angle 3. Okay. So now let's go on to page 2, which page 2 is going to get messy. So on this page, you'll notice this nice little tree diagram going from this top shape all the way down to this shape down here. We're going to name all these shapes and then say some properties. And yeah, we're going to start getting to quadrilaterals. So this very first one is a quadrilateral. So I will just let you guys know this page will there's a lot of information for this page. So try to write small and you'll see I have this all in separate ones and I'll show you my final thing. So quadrilateral at the top. The next one on the left is a parallelogram. The one in the middle is a kite. And then the last one on the right is a trapezoid. And again, we'll deal with all of these properties next. I just want to kind of name them. So then we have rectangles and rhombuses. You'll notice they are connected. They are both connected to parallelograms, meaning these are both types of parallelograms. Rhombus, you'll notice, is also connected to kite. It is a type of kite as well. And then from the trapezoid, the only type of trapezoid that's kind of special is an isosceles trapezoid, which you could probably guess what that is. And then here, if you think of a rectangle and a rhombus, once we talk about what their properties are, you'll see all of those properties in a square. It's basically if you put them both together, and that's how you get a square. Okay, so if you read this tree down, they're all quadrilaterals, right? Quadrilateral is the umbrella, parallelogram, kite, trapezoid, quadrilaterals, rectangle, rhombus, quadrilateral, isosceles trapezoid, quadrilateral, and so on and so forth. Like you just keep going down. They just are getting more specific. Okay. So let's go ahead and start looking at each one. Quadrilateral, nice and short. It's just a 4-sided polygon. There's not much to it. Quad meaning 4. Okay. And then if we move down, the next one is a parallelogram. So we'll use this symbol to represent parallelogram. The definition is a quadrilateral with both pairs of opposite sides parallel. Crazy. It's like it's called that for a reason. Now, some of the properties that we get are opposite sides parallel. That is the definition. But then we also get that opposite sides are congruent. We also get opposite angles are congruent. And we can actually prove all of this, which is nice. Diagonals bisect each other. And then also consecutive angles are supplementary. So 2 things there. Consecutive angles means angles that are next to each other, right? In the figure. So this guy and this guy are consecutive. Same with like the bottom, right? So this one is consecutive to this one. These 2 are consecutive to each other. And then you'll notice I kind of like made the mark for the opposite angles are congruent. Okay. And then the other thing is you have the diagonals, which, pretend that's a straight line. The diagonals, that's better, where they intersect will actually bisect them. Now, we don't know anything about the diagonals being the same length. That might come later for a different quadrilateral, but yeah, we just know that they get bisected. They bisect each other. Okay, so let me just clear that off so you guys don't have to see that. But again, these are the 5 things of parallelograms. And yeah, let's keep it going. All right, next, a rectangle. It is a parallelogram with at least one right angle. You've dealt with rectangles for a long, long time, so it's not something new. All angles are right, again, kind of part of that definition. And then the other property that's really nice is that the diagonals are actually congruent. So they also have all the properties with parallelograms. So you're like, oh, Mr. Rubo, I know that opposite sides are congruent. Yes. We're not listing this again because we know this is a parallelogram. Just like in parallelogram, we didn't list it's a 4-sided figure because it's a quadrilateral. Okay. So there are your 2 properties with rectangles. Next, let's go to rhombus. So it's a parallelogram again with consecutive sides congruent. So parallelogram, all those properties are true. Consecutive sides, meaning that basically all the sides are congruent. So not as many properties, but again, because all the other ones work for this, all the parallelogram properties work for this. So diagonals bisect the angles is something that is unique to rhombuses. Diagonals perpendicularly bisect each other. We already knew they bisected, but now they're actually perpendicular where they bisect. And then the last one is that 4 congruent triangles are formed when you draw in, if you were to draw in the 2 diagonals, the 4 triangles that are formed are actually all congruent. Okay. And again, a lot of this we can actually prove with some pretty short proofs, actually. Okay. And then let's get a square. It's a combination of a rectangle and a rhombus, as you saw in the diagram. So not only does it have all of the properties of parallelograms, also has all the properties of rectangles, all the properties of rhombuses, and then it also has this extra one that diagonals make 4 congruent isosceles right triangles. So rhombuses made congruent triangles, 4 congruent triangles, but specifically they make isosceles right triangles. So yeah, let's go ahead. So we're done with that tree. Let's go to kite. So a kite is a quadrilateral with 2 disjoint pairs of congruent sides. So if we look at this picture, AB would be congruent to BC, AD would be congruent to DC. Okay. Now, if we look, so it's obviously a quadrilateral, but it has diagonals that are perpendicular. Okay. So if you drew the 2 diagonals in, and again, diagonal meaning connecting 2 vertices that are not next to each other, not adjacent. Okay. Their diagonals are perpendicular. Not only that, but BD is the perpendicular bisector of AC. And if you think about it, we actually know this because B, let me actually make some marks here. So B is equidistant to AC, D is equidistant to AC, which means that that BD forms that perpendicular bisector, right? Using that equidistance theorem. So we actually kind of just prove that with just the equidistance that we've been talking about. So again, what the side going from the 2 equidistant points, so B and D, is going to perpendicularly bisect the other diagonal. Okay. So, and then the last property, sorry about that. Angle A is congruent to angle C. So we actually get that these 2 angles are congruent. Okay. And so that's it for the kites. Now we get to the trapezoid, so the right side of the trapezoid. So Trapezoid is a quadrilateral with exactly one pair of parallel sides. So if you look back at the original, you'll notice like parallelogram is not connected to parallelogram is not connected to a trapezoid, even though they both have parallel in their definition. Parallelogram has all opposite sides parallel, where where trapezoids have only one, and those parallel sides we call the bases. Okay, and yeah, there's not a lot of properties with this. We actually get a few more though when we make it isosceles. So if we have an isosceles trapezoid, it is a trapezoid with congruent legs. You probably could have guessed it. So we have the upper base, the lower base, upper base angles, right? So upper base angles would be this one and this one. Lower base angles would be these two. Our legs are congruent. Okay. We have our lower base, and then the properties that we get from this, there's 4 of them. First one is lower base angles are congruent. All right. Easiest way of kind of like imagining this is if you connected the top part to make it a triangle, an isosceles triangle, you would know base angles are congruent. It's still true with isosceles trapezoids as well, but you could also use parallel sides to prove those things. Same with the upper base angles; they are also congruent, and that's actually how I marked up the diagram. Then something interesting is that our diagonals are congruent. You'll notice though that I do not say they bisect each other. That is a parallelogram property, is the bisecting. Diagonals being congruent though, yes, that's true for rectangles, but it's also true for isosceles trapezoids. And then the last thing is the lower base angles are supplementary to upper base angles. So if you look at these two angles here, they are supplementary, which also means that these two are, and you could also go opposite angles are supplementary because you just take one upper base, one lower base angle, and you get that they are supplementary. All right, so if you're able to fit all that on the page, good job. If you had to go on a different page, that's fine. You're going to see in a second how mine looks. So you can see me trying to fit this all on one. It does get messy. So yeah, do your best. All right, so now I want you guys to go ahead and pause the video here to try out these always, sometimes, never, right? And you can use that page back there, but pause it, try it out. There's just these 10 always, sometimes, never, and then I'll go over the answers once you unpause the video. Okay, so hopefully you paused it. If not, yeah, you should have. All right, so let's go ahead and look at this statement. So it says a parallelogram is a quadrilateral. Is that always, sometimes, or never true? Well, parallelogram is indeed always a quadrilateral. Okay. And it's one of those things, again, you're getting more specific. So if you're saying that something like a parallelogram that's one step down from a quadrilateral, well, it is considered a quadrilateral. Okay. All right. So number 2, a parallelogram is a rhombus. Well, again, if you look at your last page, 5-2, mine takes a while to load, you'll find parallelogram here and a rhombus here. And the parallelogram, even though in this one it's not connected, even though it probably should be, they are, because rhombus is lower and there is a connection to it, it is going to be sometimes. Okay. A square is a rectangle. Well, every square is indeed always a rectangle. Again, square is the lowest one. So if we're talking a square, it's pretty much related to everything except for the trapezoids, right? All right, a rhombus is a square. So now rhombus is not as specific as a square. So that means it's going to be sometimes. And then number 5, I actually talked about this while we were earlier in the video. A trapezoid is a parallelogram. That is never true because they are not connected directly. right? They are connected in the quadrilateral, but that's the only thing they're connected to. All right, a rhombus is equal angular. So with this one, meaning all the angles are the same, that is not normally true, like if we're just talking a normal rhombus, but recall a square is a type of rhombus, which means it is sometimes true. It is only true when we have a square. Okay, and again, a square is a rhombus. A rectangle is equilateral. Again, equilateral, meaning all the sides are the same. Well, you guys know what a rectangle is. Opposite sides are congruent, but they don't have to be all congruent. So that's why it's not always true. But again, because a rectangle could be a square, it's sometimes. All right, 8. A trapezoid is a kite. This is never true. Again, it's that if you look at the branches, trapezoid and kite are on completely different branches. They only connect at quadrilateral. For number 9, a kite is a rhombus. Again, kite is higher up on the last page, which means we are saying something not as specific. It is possible for a kite to be a rhombus, but it is not always. And then the last one, a rectangle is a square. So that, again, rectangle, not as specific as square. So it does happen, but it only happens sometimes. And yeah, there you go. So hopefully you did pretty well with that. And yeah, thanks for watching and have a good day.